So we're very happy to have Priyadarshini Pandit from IIT Kanpur, and today she'll be giving us a string seminar on tensionless strings, closed and open. Please.
Yes. Am I audible? Okay. Thank you very much. So I will begin by. Okay, I'll try to speak. Yes. Is it okay now? Yeah. Yes, so I will begin by thanking Rajesh sir and the string committee over here to giving me this opportunity for coming here and giving a talk. So today I will be talking about tensionless strings, and in this I will talk about both the open as well as closed. You'll get to know why I'm focusing on both open and closed very soon. Okay, so the presentation will be based on the following. I would need a board light, maybe. Okay. I will mainly take the reference from these three papers. The recent one, which is written in collaboration with Arjun Bagchi from IIT Kanpur, Pranay Chakrabarti and Sankadeep Chakrabarti from IIT Roper, Stefan Fredenhagen, Daniel Grumiller from University of Vienna. And these two papers written in the last 2 years was in collaboration with Arithro Banerjee, who is in BITS Goa, and Ridankar Chatterjee from IIT Roper. And for the review part of the talk, I will be following these three references mostly. Okay, so the plan of my talk would be, first I will give the classical aspect of tensionless strings, and this will include both the closed sector as well as the until now unexplored open sector. Then I will give a brief review of quantization of tensionless closed string, because quantization of open string has not been done yet. Then it will be followed by impact of circle compactification of target spacetime. If we compactify the spacetime dimension, then how does this affect the mass spectrum and hence the symmetry? Same goes with the addition of Kalb-Ramond background to the target spacetime, and how does this affect the mass spectrum and its symmetries? And then I will close with giving some conclusion and future directions. Okay, so first I will give a brief review of tensionless limit or tensionless strings. We all know that it generalizes the notion of point particle to one-dimensional string as the fundamental object. And the non-interacting string theory is characterized by its only free parameter, which is the tension, and this is related to the length square of the string. And hence we can take two different limit or two extremely opposite limit on this tension. First being tension very high, which is the point particle limit, and this corresponds to the low energy limit of string theory. The other limit, which is the diametrically opposite limit, this is the tensionless limit. And since the tension is inversely proportional to the square length of the string, so this is otherwise called extreme stringy limit, because the length of the string has grown very long. And since this is the opposite of this, we can think of it as the ultra high energy sector of string theory. This was first studied by Child back in 1977. However, in 1994, this was developed by Isberg and collaborators. I will show where we go. Okay, so first, if we want to know about a theory, we would like to know what is the action of it. It is not mandatory to know the action, but here we will follow these footsteps of string theory. So we would like to construct the action for it. So for the construction of the tensionless action, I would start with the Nambu-Goto action, and for which the action of which is given in equation 1. So for those of who don't know about that action, so So the action for the point particle, if we consider a point particle with some parameter lambda, this is proportional to the invariant length of the string. Okay. Similarly, if we generalize this point particle to one-dimensional string, then this will trace the worldsheet for us, where this is sigma and tau direction, and the action will be the proportionality constant could be found as d tau, or this also can be written as so when we talk about the string, this will be proportional to the invariant area. Okay, and the proportionality constant will be where gamma alpha beta so here whatever I have written, this T is the tension, which I showed you the relation, and then tau and sigma are the worldsheet coordinates, and x mu are the space-time coordinates. Okay, now we want to construct the tensionless limit. So we take tension to 0 over here. However, if we see that if we take the tension naively to 0, the entire action would vanish. So we are in a trouble. However, we encounter the similar problem when we try to take the massless limit in the relativistic point particle action. Here also mass is sitting outside, and if we take the tensionless limit, we are going to face some trouble. And we know how to solve these kinds of systems. These are the constraint system, and hence we solve them using Hamiltonian formalism, where we introduce the auxiliary field E and introduce the auxiliary field to form an classically equivalent action, which is given in equation 3. And here you can see the mass is no longer sitting as a multiplicative factor for the action. However, it has gone to inside, and we can safely take the massless limit over here. The similar procedure has been followed by Isberg and collaborator back in 1994 in order to construct the action for tensionless strings. So they compute the generalized momentum, and then the constraint followed by those momentum. And then they construct the Hamiltonian. These are the constraint followed by this momentum. And lambda and rho are the Lagrange multipliers. Now, since we have this Hamiltonian, total Hamiltonian, we can find out the Lagrangian for this system. And then from the Lagrangian, we can formulate the action, which is given here. And you can see here that here we had P. However, when we go to Lagrangian framework, we don't have P over there because that is the coordinate for the Hamiltonian. So we integrate out the momenta, and the action we are going to get is of this form. Here also you can see the tension no longer now sits outside. However, it is sitting inside, and we can take the tensionless limit. This action can also be viewed in a very familiar form, which is the Polyakov form, in the following manner, where G alpha beta is identified as the following metric. Now, since we are considering tensionless limit, which is a singular limit, it should come up somewhere, right? So here you can see that if we take the tension to 0 over here, the determinant of the metric vanishes. So the signature of tensionless limit is coming over the worldsheet of the tensionless strings by giving us the degenerate metric, or the determinant is becoming 0. So now we take the tensionless limit by replacing T root over of minus G alpha beta by V alpha V beta, which is a rank 1 matrix. And V alpha and V beta are the vector densities written in terms of rho and lambda, which are the Lagrange multipliers. So we end up getting the action, which is of the following form. This is also called as ILST action by the name of the authors, Isberg, Lindstrom, Sundberg, and Theodoridis. So now we end up getting the action intrinsically. We can start, since we have the action now, we can vary this by the standard variational principle, and then we can find out the equations of motion, the constraint equation, the boundary terms, etc. So first I will start with the classical analysis. Here we vary the action. The variation of the V alpha will give us the constraint equation. However, the variation with respect to x mu will give us boundary term as well as the equation of motion in the following manner. The sigma boundary condition tells us what type of strings we are dealing with, whether it is closed or open. If sigma is periodic, that gives us the closed string. If it is not periodic, then it will give us open string. And the equation of motion here will take the following form. Equation of motion as well as constraints will take the following form. Now this, under gauge fixing, because of the presence of the diffeomorphism in the system, will simplify to the following form. This is the equation of motion. Simplifies to under this gauge where V alpha is V0. So this is analogous to the conformal gauge we fix for the case of usual string theory. There G alpha beta becomes eta alpha beta. So for general string theory, G alpha beta becomes eta alpha beta. Here V alpha we are considering to be this, and the equation of motion is this, and these are the two constraint equations, which is equivalent to the component of the energy momentum tensor. This one? So gamma alpha beta is this. Yes. Okay, now we have the equations of motion, we have the equation of motion, we have the constraint equation. Now we would like to solve the equation of motion and get the mode expansion which will solve this equation. So the mode expansion which solve this equation of motion is of this form. Here A and B are the oscillatory modes. However, and B is the momentum of the string. However, the Poisson bracket of A and B, you can see that they do not form the harmonic oscillator algebra. So what do we do in order to get the harmonic oscillator algebra? We define new modes, which is from the combination of linear combination of A and B. You see here.
These are first class constraints that you don't put in a gauge fixing condition to make it a second class constraint? Normally, so how do you, okay, anyway, usually you're going to explain.
Yes. So I will not be talking. So the gauge fixing condition I have already showed you, which is this V alpha.
Typically, when you have first class constraints to begin with, and you put gauge fixing conditions, then the gauge fixing conditions and the initial first class constraints together, they form a second class constraint, because if the gauge fixing is good,
Yes.
then the determinant of the cost of is between all the constraints, including gauge fixing, they should be non-singular, and therefore it's a second class system, etc. But maybe it doesn't make a difference for you.
Might be, because again, we will be having residual symmetry left over here. Yes, which, yes. Okay, so as I showed you that the sigma boundary condition will tell us what kind of string we are dealing with, whether it is closed or open. So first we will be dealing with the closed condition. Here the sigma is periodic in nature, and hence when we put this condition to the mode expansion, the linear term in sigma would vanish, because in order to satisfy this. So the mode expansion will not have this particular term, and then we'll have all of the rest term. This is the Poisson bracket relation of C and C tilde, which tells us that this is the harmonic oscillator algebra. Okay, so now we will move on to find the constraints equation. And the constraint, we were having two constraints, which can be written in terms of the generators. So in the usual string theory as well, we have gauge symmetries, which were diffeomorphism and while, and we fix them. After fixing, we are going to get G alpha beta, zeta alpha beta. However, again, the action of the string theory that has this residual symmetry left over, which on the worldsheet will give us two copies of Virasoro algebra. For this case as well, even after gauge fixing, we will be left with certain residual symmetry. The generators of those symmetry will be Ln and Mn, which will, in the form of the C and C tilde, will have this form. And they will close to form, this I have written the classical algebra, the BMS3 algebra, or two-dimensional conformal Carrollian algebra. So far what I told you is that for the usual tensile theory, the worldsheet symmetry algebra was two copies of Virasoro. However, for tensionless theory, it is two-dimensional conformal Carrollian algebra or BMS3 algebra. All of these results, so everything till now I was showing from the perspective of the intrinsic analysis. We constructed the action, from the action we found out the equation of motion, constraint equation, symmetries, etc. However, since I was showing you that this was a limiting analysis from the usual string theory, so we would also be able to find out all of the results by taking the tensionless limit on the string theory values, string theory classical results. So in order to check that, we see that we can derive all the classical results by directly taking tensionless limit on the tensile results. And this on the worldsheet can be thought of as tau going to epsilon tau, sigma to sigma, and alpha prime, which was tension, varies in the following manner, where epsilon is small. Okay, now so for tensile case, the mode expansion will have alpha and alpha tilde. I will show later the mode expansion of tensile. And I showed you that the mode expansion for tensionless case will include C and C tilde. And they are related to each other by this following transformation, which is the Bogoliubov transformation. This limiting analysis can also be seen, or it is reflected on the symmetry algebra, by the following relation. As I was showing you that this flat ln and mn were the generators of the constraint equation which I was showing you, generators of the symmetry which was BMS3. This curly ln and ln bar are the generators of the two copies of Virasoro algebra, okay, which was coming from the tensile case. So when we take the limit from that, we can get the tensionless residual symmetry algebra on the worldsheet. Okay, so story so far, we had tensile theory, which was given by Polyakov action. We formulated the ILST action, which is the action for the tensionless theory. The mode expansion for tensile theory was given by this particular equation, where alpha n and alpha n tilde are the modes, oscillatory modes. For tensionless, I already showed you Cn and Cn tilde are the oscillatory modes. Now from the boundary condition, first boundary condition of sigma, which is periodic in nature, we get closed string. For the tensile case, we will get the symmetry algebra to be two copies of Virasoro, which is of this form, L and L tilde. And for the tensionless case, so this is all about tensionless. For the tensionless case, we are going to get the BMS3 or two-dimensional Carrollian conformal algebra. Okay, so now as I told you that for sigma boundary condition, we have two kinds of string. One is the closed string where periodicity boundary condition was there, and the other is the open string, which was governed by this two condition, the Dirichlet and Neumann. The Dirichlet condition tells us that the end point of the string are fixed. So the endpoints are fixed and they do not move. However, the Neumann condition, so if we consider this as the space-time and we put the Dirichlet condition over z direction and Neumann condition over this floor, then the string endpoints could move on the floor. However, it cannot move up and down because Dirichlet condition is put. Now, all of these were good for the tensile theory. What about the tensionless open string? This was not done. So when we consider tensionless open string, what does that put constraint on the mode expansion? For example, for open string of tensile theory, the left moving and right moving modes are related to each other by this condition. What happens when we go to tensionless case? And the most important question is what happens to the residual symmetry algebra when we go to tensionless open string? Because for the tensile open string, from two copies of Virasoro, we get single copy of Virasoro. Now it was a question till long from almost 1994 that, so here we were having ln and ln bar. So these were Virasoro generators and ln and mn were BMS generators. And we could just make the combination, linear combination of them by to get the ln and mn or the BMS3 generators. If we don't have this ln bar, because I'm telling you that we have only one copy of Virasoro generator. If we only have any one copy, then how to formulate this algebra? So that was a question that was long not solved. Then I will give a brief review of quantization of tensionless closed string, because open string quantization has not been done. Here I will just review because this part has already been done. So this here I will show that from one classical theory, we can get three different quantum theories based on three different vacua. I will explain all of this. This is just the main insights I'm showing. And then I will talk about what happens when we compactify one of the space-time dimension and how does this connect to two different theories, or is there any duality or dual theory which is coming under some different corners of string theory. Okay, so the question of open string was solved very recently, where we find the emergence of new algebra. Okay, so this is the tensionless action. This is the variation which I showed you. And from the boundary term, we are going to get the open string. And here you can see that the boundary condition, I showed you that for tensile string, we had two boundary conditions, the Dirichlet and the Neumann. Here we have, instead of two, we have three boundary conditions, which is n alpha v alpha. Here this is purely geometric in nature. So these are the n, and this is some 1, 0. And the other as well. So this is very interesting because since in literature we have this, the closed string and open string becomes indistinguishable when we take this tensionless limit. So this particular boundary condition can be indicative of that, because if we consider this boundary condition, we don't need to consider these two. Anyway, one is 0, then the other we don't need. So this is very interesting, but we have not solved this. We have started with the Dirichlet condition. I'll show why, I will tell why. And okay, so the equation of motion we'll be solving later. So the important part of this slide is that we have three boundary conditions as opposed to two. In this paper, we started with Dirichlet boundary condition because we also wanted to get the algebra and all sorts of results from the limiting analysis. If we consider this null boundary condition, then there will be nothing to take limit from, what we understood. And hence we started with this Dirichlet condition. And when we impose this condition on the mode expansion, as I was telling you that alpha n and alpha n tilde were related, similarly here we will find that Cn and Cn tilde are related to each other. And hence in the mode expansion we will only have either C's or C tilde and not both of them. And this will affect the algebra as well. Now we will move to the most important part, which is the symmetry algebra, which we get from the constraint equation again. Here Pn and On are the generators of the symmetry, residual symmetry algebra. This is just the mode expansion form of that. And the new algebra what we got from here is that they follow the following algebra, which is definitely different from the Carrollian conformal algebra. So for closed string, we were getting Carrollian conformal algebra. For the open string, we are getting boundary Carrollian conformal algebra, which is different from, and this was not seen till today. Let us understand a bit more about this algebra and how do we get this. Okay, so for the closed string case, I showed you Ln and Mn were the generators of the residual symmetry algebra, which we can also get from the UR contraction, as I showed you here as well, by this particular form. And Ln and Ln tilde on the cylinder takes the following form. Now we have cylinder, okay. This was the cylinder. Now we put boundary to that cylinder. Now when we put the boundary, the invariance along this boundary will be broken. Invariance along this sigma boundary will be broken, okay. So the operators or the generators that leave the boundary invariant cannot have a non-zero action of sigma at the boundaries, okay. So, and we devise a set of generators that will satisfy that condition, and we end up getting On and Pn, which were giving us the residual symmetry algebra, which we found to be this. And we can see that for sigma equal to 0 and pi, we don't have any del sigma term. We can also obtain this boundary condition, Carrollian conformal generators, from the single copy of Virasoro generators in the following manner. So there used to be some questions on this particular part, that when we go from 2 copy of Virasoro, which is the tensile closed string, to 1 copy of Virasoro, we have reduced the number of generators, because we were having ln and ln bar, and then for the open string, we only have ln. What happens here? Are we reducing the number of generators over here? Indeed, that is true, because you see that here the ON and O minus N are related to each other, and P and P minus N are also related to each other. So if we know ON, we can also get the O minus N. So in this way, we can form the tensionless open strings, and the symmetry generators, or the residual symmetry of that world sheet would be the boundary Carrollian conformal algebra. All of this can also be obtained from the limiting analysis. I'm not going details into it. So
you have to restrict to n greater than or equal to 0 or something like that. You will in your algebra.
Yes. And because otherwise we will be getting the other.
So then that algebra gets a little more. You had some m minus n mode numbers, so you have to put some modulus signs and so on, right? I mean, the algebra will look a little bit different, no? In the UN and
I get
PN
your
algebra.
point.
So this is not true for you want to restrict it for m and n positive only, and so yeah, okay.
The mod would help, yes.
When you say that you devise a set of generators which don't have n segment terms at the boundaries, is this imposed? For example, the silent segment of DON, is that something you put in by hand or something that you get?
No, this ln I showed you here, this ln has this form, and we take the linear combination of ln and L minus n.
What?
We are going to. Yes, exactly. Yes, so we obtained for the tensionless case the boundary condition, the constraint it puts on the mode expansion, and the residual symmetry algebra was boundary conformal Carrollian algebra. So earlier we had tensile closed string, which was on the world sheet. We had 2 copies of Virasoro. We take the UR limit. We had 2-dimensional Carrollian conformal algebra for tensionless case. Here we have, when we put the boundary condition, we have tensile open string where we have single copy of Virasoro. And now with this discovery, we close this square and we get tensionless open string, which has the 2-dimensional boundary Carrollian conformal algebra. This can also be seen in the following manner. For tensile closed string, we study this using 2D CFT. When we go to open string, we study that using 2D BCFT. When we go to tensionless theory, we study this using 2D Carrollian CFT. And for open string, 2D boundary Carrollian CFT. Okay, so now I will move on to quantum analysis. Quantum analysis will not have any discussion about open string. Open string was still classical analysis, because wherever I have given this talk, everybody gets confused with the quantum analysis of open string as well. So that's why I told you earlier. Okay, so when we go to quantize the tensionless strings, I told you that we are going to get 3 different quantum theories from just single classical theory. So the energy, so in classical sector, I showed you that T1, which was the component of energy momentum tensor. So we were having T1 as x dot square equal to 0 and T2 as x dot x prime equal to 0. So they were vanishing. However, when we quantize the theory, these components of T1 and T2 are promoted to operators, and hence we cannot just make them 0. we demand all the matrix element of the operator in the physical Hilbert space to vanish. Okay, and this T1 and T2 can be written in terms of generators in the following manner. Ln and Mn are the generators of this, and Al and Am are the normal ordering constants. This is exactly same as what we do for tensile theory. There also we have A, which we fix later to be 1, and here we will see that this will also be fixed by demanding Lorentz invariance. Okay, so let us consider that we have a generic constraint Fn. So, and the sandwich condition can be satisfied by 3 possible conditions. One could be the right hand action is 0, which is the which gives us the highest weight representation. The other could be the right hand action is 0 for n, all n not equal to 0. And the third could be this non-zero, however the sandwich is 0. And if we, so this is just for one condition, one constraint, and we have Ln and Mn as 2 constraints. So we will be having, for each constraint we will having 3. So there will be 9 different conditions which can give us different quantum theories. However, out of 9, only these 3 are consistent with the BMS3 algebra. This computation I can show you maybe later because this is a bit lengthy to show. But just I can tell you that if other than these 3 conditions, if we are going to take some other condition, for example, let's say we are considering this is the highest weight because the right hand action is 0. If we are considering Mn physical is 0 and Ln physical is also 0, then that would restrict our set of constraint, set of oscillators to, so there will be some relation. So this will reduce our set of oscillators to just one set of oscillators, and hence in this way all the other 6 could be ruled out and we are left with only these 3 kinds of generators or kinds of theories. And this result in three different quantum theories on 3 distinct vacua: the flipped vacua, the induced vacua, and the oscillator vacua. Here this not equal to 0 means the sandwich is 0. This was shown by Bakchi and collaborator in 2020.
So if you were in this thinking, you just said that this you do the second, sorry, the first of what you will have, like you put the value or something.
Yes.
Why does it become interesting to consider 3 different?
Yes, so there was a paper very recently by Arjun and Sahin Sikh Jabbari that in usual tensile theory as well, we can impose this weaker constraint. So these are definitely the weaker constraints, that the right hand action is non-zero, but the sandwich is 0. But there, till now, there has not been any relation between which tensile theory is giving us which tensionless theory. But there also we can consider the weaker constraint. However, we just, in general textbook, we just consider the highest weight.
But in this constraint, I mean, it will match with the BRST, the spectrum we get from the BRST, right? And maybe if we impose weaker conditions, we may not get a match with the BRST result.
Yeah, so I'm thinking that QED where you do Gupta broiler as opposed to whether you do this QED, you get the same answer. But you're saying somehow Gupta broiler need not be the case and you can do something more centers. How you consider this with all that together?
Maybe that part I don't know because that has not been studied a lot. But I just want to say that the weaker constraint has also been studied for the tensile case. And this oscillator induced, and this flipped one, okay, I will say later. Okay, so I will give the brief introduction for all the three vacua and then I'll move on to my own work. So for the oscillator vacuum, this is the weakest condition because the right hand action was non-zero, however the sandwich was 0. And here the AL and AM are the normal ordering constant, and that was found to be, AL was found to be 0 and AM was found to be 2. This also comes from the similar demanding of the Lorentz invariance where A was found to be 1 and C was found to be D for tensile case. The vacuum on which this theory is constructed is the oscillator vacuum, and we define it in the following manner. And the mass spectrum of a level matched physical state, what the level matched I'm saying because this, when we put this L0 on the physical state, so when we apply this equation, then so L0 will have, these are the number operators. So we will see that only the level matched states are the physical state and not the other way. Hence, we will only be considering the level match state, and the mass spectrum for the level match state is found to be this. For the tensile case, it was 1 by alpha prime, 1 by alpha prime n minus 1, n minus a. Okay, now induced vacuum. That was the oscillator. This is the induced vacuum. This, if we take the tensionless limit directly of the usual tensile string theory, we get the tensionless string theory on the induced vacuum. And the physical state condition, as I showed you, that this is 0, however, the sandwich is 0 for Ln. And for the tensile case, as I'm saying that this action we are going to get from the direct tensionless limit of tensile action. So this was the vacuum. So this was the vacuum condition for tensile case. If we take the tensionless limit, there will be relation between A and B. As I showed you that there was this Bogoliubov transformation between C and alpha. In C we have A and B. So there will be some relation. I think I remember. Okay, so similarly for this, we have if we see this, then the vacuum condition will become the following. Bn will be 0 because if you multiply root of epsilon over here, then you'll see that Bn on this is 0 and B minus n on this is 0. So Bn for all n not equal to 0 is 0 and B0 is the momentum. And B0 square, since this is the momentum, we will get k square, which is the mass square. And this is 0 because Am is 0 for this induced vacuum. So the mass since Am is 0, so in M0 we have k square plus n tilde. So that's why since this is 0, we have mass 0 over here. What does that means? So all the perturbative physical tensile states that condense to the induced vacuum resulting into a worldsheet Bose-Einstein-like condensation. This is not our work. I'm just showing it for what happens when we go from, so since I was telling you that from tensile theory, if we take the tensionless limit, we will end up getting tensionless induced vacuum. So I showed you here that all the mass are becoming 0. So this can be thought of as Bose-Einstein-like condensation, and this was given by Bakchi and collaborator in 2019. Yes, exactly. And this, they also say, have studied this, that this can be thought of as the closed string becoming open, because all of them are, I am not going much detail into it. Then the last one, which is the flipped vacuum. The tensionless string theory constructed on the flipped vacuum corresponds to the highest weight representation. You can see this from the following physical state condition only, and AL and AM are found. The flipped vacuum is this. The Cn acting on this is 0, and Cn tilde, which is C minus n tilde, on this is 0. This can be thought of as the limiting analysis from the twisted tensile theory. We have also, so we have string theory, usual string theory, and then we have twisted string theory, where the anti-holomorphic part, for twisted string theory, we have alpha n on vacua is 0. However, alpha minus n tilde on vacua is 0. So this is tensile theory. There exists this kind of theory. This is the tensionless limit of this kind of theory, where the anti-holomorphic part has been flipped. And because the AL is 2 over here, the physical state condition imply that only level 2 state is physical and they are massless. This is not of that relevance, but okay. So now we'll move on to compactification. How much time do I have? I have or okay. Okay. Now, by impact of compactification, I mean that if we have space-time, so we are dealing with d equal to 26, and one of the space-time dimension, which is, let's say we consider x25, we compactify them. So if we compactify, we have certain momentum in that compactification direction, and W is the winding modes. If we quantize this theory, then W become the winding mode. This result in, so as I was showing you that X will have, yes, I just use once. So X will have X plus something in the linear combination, the linear in sigma, and some, so this was A0, this was B0, and this was tau. And I was telling you that this will give us, and these are the oscillatory modes, A and B. So this was something I was showing you as the mode expansion. And I was telling for the closed string, we will not have this particular linear term in sigma. So here we will see that since we have this compactification, these A0 and B0 mode will change. Okay, they will have certain, because of this 2 pi r omega, we will have A0 and B0, since it is the momentum, so that will also get modified. Why am I showing you this? Because the 0th mode are responsible for finding out the mass. Since A0, B0 changes, so C0 and C0 tilde also changes. We have the relation between them. And the modified mass spectrum will have, so earlier it was, I was showing you that it is 1 by C prime 2n minus alpha m. So this will be there. Along with this, we will have this extra addition of this term, this k square by r square, because of the momentum. However, when we go to tensile theory and compactify one of the space-time dimension, we will see that we have these two terms. Okay. However, we don't have this omega square term here. Are we doing something wrong? Because here we have T duality, which is very distinctive symmetry of the tensile theory. We don't seem to have it here. T-duality, I would say, okay, so T-duality is something which is, can I rub this? So in T-duality, we see that if a string theory is defined on a radius, on a circle of radius r, is T dual to string theory defined on a circle of radius alpha prime by r, where alpha prime has the dimension of length square of the string, and the k and omega modes are interchanged. Here, we can see that this interchange can lead us to the same mass spectrum. However, the same thing is not possible here. However, we also know that from the string theory, if string theory compacted, so what is T-duality? String theory compactified on a very small radius, it's alpha prime by r, is equivalent to string theory compactified on a large radius. We know from literature that when r is very small compared to the length scale of the string, then we get the momentum dominated part of the mass spectrum. And when r is very small, very large, we get the winding dominated part. Now I showed you the comparison between r being very small, r somewhat small, and r large. Now we will do the same thing for the length of the string. If we have a line and we want to make it shorter without just erasing it, what can we do? We can draw another line over here. What is the reason I'm showing this? So here we can fix now r, and we can say that, let's say we have, so for r very, very less than length of the string, we have momentum dominated part. And for this, we have winding dominated. Okay. Now we fix the r, we don't change r. And we know that the length of the string for the tensionless case is very large. So the thing we are getting, which is just the momentum dominated, is not wrong. And hence, we can get the thing what we got there. Like I showed you that we were getting whether this was wrong, right? So we can verify it from here also. Okay, this is the last part of my talk where I will show you that if we introduce the background B field to the space-time, then how does this change the mass spectrum?
The upshot of this T-duality is that, like when I'm in tensionless limit, I basically don't even expect to see the T-duality in mass spectrum.
There is little more to it. I'll show you here after this. Okay, so we introduce the B field. This is the tensile case. We introduce B field. In order for B field to survive, we have to also scale B in order to survive this epsilon of T. And we get this action. So since this is the addition of the constant B field, so the equation of motion, symmetries, stress tensor, everything remains intact. However, the only thing which changes is the canonical momentum. And we find out the total momentum. Here you can see that the B field, introduction of B field can only take place if we have compactification dimension. So earlier I was showing you there is circle compactification. In this particular work, what we have done, we have generalized it to TD, torus, and introduced the B field. And this is the momentum which becomes of this form. These are just technical details. And here also we need to know what is the change in the zeroth mode, because that will give us the mass spectrum. Okay. Now we will move on to quantum analysis. Here the quantum analysis will be same because we are introducing the constant B field. And we are going to get three different theories: oscillator, induced, flipped. However, the mass spectrum will be looking like this. for all the three cases. So for the circle compactification, I showed you that the extra term or the modified mass spectrum will be this. Here the modified will be this along with this extra term. This can also be written in the following matrix form. Okay, and this is something which is a bit new. So this is the compactified string mass spectrum is connected to the 2D dimensional double field theory, where G plays the role of inverse matrix, which is determinant of G equal to 0. Now, what is 2D dimensional double field theory? So double field theory is nothing but, okay, so we have T-duality as a distinctive symmetry of the string theory, because we need extended object to wind. In the field theory, how to incorporate that symmetry, that is the main role of this double field theory. And they do this by introducing dual coordinates. For example, we have xm, we have xm for the compactified dimension, and the momentum can be related to this. We will introduce some dual ym or xm tilde for the winding modes, because we need winding modes in order to have the T-duality in the theory. So that's why, since the coordinates are doubled, this is called the double field theory. And we have not gone much detail into it, but we have seen that this generalized symmetry, generalized metric, this is called the generalized metric, that is similar to the form of the 2D dimensional double field theory. However, the difference is that there the determinant was not 0. Here we have the determinant to be 0. Okay. All of these results we can also get. So this is the generalized metric from the double field theory. If we take the tensionless limit, we are going to get our result. This will not be there, because you see alpha prime, if we take C prime by epsilon square, so this will cancel this, because B is also scaled. So this will survive, and we will get the one what we got. Okay, so I showed you that there we are facing some trouble with the T-duality when we go to the tensionless case. What happens when we introduce B field? Does the symmetry remains intact, or does it also breaks? So when we introduce B field to the tensile string theory, the symmetry becomes ODDG symmetry. There we were having T-duality, here we have ODDG symmetry. What is that? So that consists of basis change, discrete shift symmetries, and factorized duality transformation. I will not go very deep into it, but just to tell you that basis change is, so whenever we have compactified system, we have K and omega. We have K and omega. So basis change is something where we are changing K to C K and omega to omega C transpose inverse. If we do this, the mass spectrum remains intact. The discrete shift symmetry transformation is, we are changing Bij to Bij plus Nij. This is some discrete shift symmetry, and again the mass spectrum remains intact. What about this factorized duality transformation? This gets broken. As I was showing that their T-duality was getting broken. Here the factorized duality transformation is somewhat getting broken. If you want, I can show you explicit computation, but that will take some time. So in just 1 minute, I can show. Factorized duality transformation is, let's say we have, okay, so I was showing that omega and K, and then this was the G, and then we had omega K. This was mass spectrum. Okay. So when we have more than one compactification, we will have omega 1, omega 2, omega 3 in this way. and similarly K1, and then G, and then factorized duality transformation is something which will exchange just one of omega and K. Why am I focusing more on omega K transformation? Because for T duality as well, I was saying that the theory defined on R and alpha prime by R are T dual, provided K and omega get exchanged. So same case here. If one of them gets exchanged, then we are not going to get the duality, and we are going to get something which is here. Okay, so what is here? So this thing I can show explicitly maybe after I finish, or okay, first let me tell you this. Let's say we have a theory at so the gist of this slide is that we are going to some other corner of string theory. I can show you that. Let's say we have a theory in, so this is string theory, all of there. We consider one theory here, which will have tensile theory. Tensile theory we will consider, where we will include B field on the diagonalized torus. Let me not confuse you with lots of jargon. So here we have a torus, which is diagonalized. Okay. We now take the factorized duality transformation on this particular theory. We are going to get something. That something is tensile theory without B field. The B field will be 0, and the Gij will not be remain diagonal. So this was, let's say, 1 by R square. This was torus, and here we will get all of them, not just a diagonal. So from factorized duality, we are staying in the same string theory regime. However, there will be no B field, and the metric Gij will take this form. Now we take the tensionless limit of this theory, which we were doing. We are going to get certain theory, let's say C. Okay, tensionless theory, here we take tension to 0. B also scales, as I was saying, this is B by epsilon. So we scale in this manner, and we get certain theory C. When we take the tensionless limit of this, we should get some theory over here, which should be T-dual to each other, right? It's not T-dual, but factorized duality to each other when we put the transformation. However, this is not correct. When we take tensionless limit of this and we put factorized transformation, factorized transformation means one of K1 is going to omega 1, other K2, K3 that remains intact. There is no change between them, exchange. Here we are getting some theory. We know what this theory will be because we know what C is. We can follow this transformation. We get certain theory, which is D. This, however, is coming from a limit of A, which is not the tensionless limit. However, this is something which is the degenerate torus. If we make the torus to be degenerate, then we are going to get this theory, not when we take the tensionless limit. So from this, and also from the T-duality transformation, we can think that there might be some corner of string theory, which we don't know, which this can connect to. Okay, there is explicit derivation I can show if you like. Would you like to see the explicit derivation?
Get the idea, because you can take the similar limits.
Yes.
They will break the
Maybe I can show you just at the end. This is just the end, and I can. Okay, so the conclusion and future direction. So we studied the classical tensionless open string for the first time and initiated a study of Carrollian CFT with boundaries. This can have many applications, and we can go for the representation theories, and we can see what this gives us. It would also be of great interest to explore the quantization of open null string. We have not quantized it yet. The construction of D-brane in the tensionless theory and supersymmetric version of open null string will also be very natural next step, which we have completed just recently. Then this null boundary condition, as I was showing you, if that condition is satisfied, we don't need the other two. So it seems that the open and closed string become indistinguishable in this limit, and this boundary condition is the indicative of that. This can also be thought of as the means that we can also study about the flat version of ADS BCFT correspondence. The flat version would be flat space BCCFT correspondence from the analogy of the ADS CFT correspondence. If we consider Carrollian case, would involve this symmetry. We observed a hint of existence of degenerate limit of double field theory in our analysis. It will be really interesting to explore more on this avenue, because what is the degenerate limit of double field theory has not been studied at all. We also notice a subset which is the ODDG transformation, which might possibly connect the tensionless string to some other limit of string theory with degenerate torus, which I was showing you. Other limit with degenerate torus. The limit could be that, not this.
This degenerate torus, I mean, this simply means that in mass, that matrix has zero element.
Yes. If we consider that limit, then only we are going to get the duality, the theory when we put factorization.
It's the target space.
Yes.
Like if I have n dimensions compactified.
Yes, because we are compactifying dimension on the target spacetime only. Okay.
Somehow, okay, maybe degenerate. It's I don't know. Should I think of it geometrically that?
Here in the tensionless string on the worldsheet also I showed you whatever we get G alpha beta, that is also degenerate. We have not studied much about it, but we get the hint of that. So it will be very interesting to have the intrinsic analysis of that. These are the motivation why we study tensionless string, because in the Hagedorn temperature, very large temperature, in that the partition function that diverges, the partition function is some VE rho e to the power minus beta e, and this for string theory, this grows as beta h e. So if we'll see that for t greater than th, this diverges, and a tensionless string is thought of as the candidate for string theory beyond this Hagedorn temperature. So what I want to say is, in string theory, probably we cannot explain something beyond Hagedorn temperature. However, at the Hagedorn temperature, the effective tension becomes zero. That means it might be possible that we can explain things using tensionless strings. Gross and Mende gave this, that in this tensionless limit, the string scattering amplitudes become very simplified. And this is very recent paper by Steiberger and collaborators, where they showed that there is a correspondence between the celestial open string amplitude and the open string amplitude in the tensionless limit. So this can give us, this connects the flat space holography with the tensionless limit. Yes, this is. And for the one which I was showing you, the cat picture, These are the basis change metrics. You see where K is changed and omega is changed in this way. Discrete shift symmetry, B is changed in the following manner, and the mass spectrum remains intact. Factorized duality transformation, here EI has been introduced. That means only one of them changes. And we cannot write, if we change one of them, we cannot write the metric, generalized metric. This G had certain form, B G inverse B, G inverse B minus B G inverse and G inverse. If we do this factorized duality, we cannot write the mass spectrum in this following manner, because anyway we will get something which is this 0, and hence everything becomes 0. That I will show you. Let us consider one example. Here compactification is on torus, okay, and this G is this. Maybe it is not visible here, I can write it for you here. So this G was B G inverse B, G inverse B minus B G inverse and G inverse. Remember this generalized metric. Now this B, yes, what is B? So B is B R1 Ri Rj epsilon. B is this, and G is the metric R square, R1 square, R2 square. And then we can form something like this from this, okay. Now we apply this GD2. What is GD2? GD2 means these two get exchanged, okay. I'm not going detail how we got this. This is also easy to see, but this tells us that K2 and omega 2 gets exchanged. Now what do we get? G prime, which is of this form, diagonal. Now if we want to write this in terms of this, you see that if this part is 0 completely and this is not 0, that means G inverse is not 0. However, B is 0. If B is 0, then this should also get 0. However, this is not. Hence, this is not the same theory we are getting from here. Okay, because that cannot be written in that form. Now, since the metric cannot be written, cannot be consistently expressed in this form, so this cannot be linked to any tensionless string action. Now we will see, now I will tell you this part from the tensile theory. In tensile theory, if we consider the same thing, the generalized metric is this. And if we take the factorized duality GD2, which was same as the one I showed, then we are going to get this kind of metric, which is exactly same as the one we got there. However, when we relate these two, we will see that Bij is 0 here, Gij is this. Okay, and this can be related to the one which we got here as the, so here we got G prime as something here, something here, something here, and these two were 0. So that could only be get if we take R to epsilon R, B to B by epsilon, R2 remains fixed. So here if we are taking that torus to be degenerate, one of the radius is becoming epsilon, then only we are going to get this kind of generalized metric. So this might tells us that there is indication towards duality web, which is not the same as tensionless limit. This is something else. This was the example which was done explicitly. Yes, let me go back.
I was wondering whether the B field, you have looked at the open string with B field, like at least in the Dirichlet conditions that you studied. But that may be interesting long ago, Seiberg and Witten had studied with the constant B field and shown how you get a non-commutative theory when you switch on a constant B field. So if you look at the world volume theory of the brains, instead of ordinary angles, you get non-commutative angles. So I don't know, it might be interesting to study the open string version also with
of the B
and
field.
see what happens to the world volume
Yes,
theory.
yes.
Following that Seiberg-Witten analysis, which is sort of using many of these ingredients, but now in the open string sector.
I have known one thing which was given by Gomis and Uguri, that introduction of B field and the duality between non-relativistic open string, a non-relativistic string theory with the DLCQ string. So introduction with the open string, I will look at it maybe.
Yeah, so this ODD, that means that there is now a subset only of the ODD that is.
Yes.
So that subgroup will be some kind of also a discrete, it's probably mathematically you can say what kind of subgroup it is. No? It's some kind of null subgroup or something like that.
Yes, might be. But this factorized duality also, if we are doing for even cases, then the mass spectrum is invariant. However, just the odd if we will do, then that is getting odd being the exchange between, let's say I am exchanging. Yes, if 3 of them or 1 of them we are doing, then only the symmetry breaks. Otherwise, that remains intact.
Then let's thank you,
Thank you.